أعوذ بالله من الشيطان الرجيم. Bismillahirrahmanirrahim. Welcome to the second lecture of week 7. So we have been discussing the deep drawing operation of the sheet metal working process. So in the last lecture we discussed some fundamentals of the deep drawing and the parameters that are required to determine the feasibility of a particular deep drawing operation. So in this lecture we are going to see some specialized conventional drawing operation, and then we will move towards some other sheet metal processes that are performed on the conventional presses but with the metallic and the rubber toolings. So if we start with some other drawing operations, the first one that comes is the redrawing. So this one is termed as the redrawing operation. So what the redrawing is, if the shape change required by the part design is too severe, like if we have a very high amount of deformation that is to be made in the blank, then the drawing operation is not performed in a single step, rather it is performed in multiple steps. So the second drawing step and any other further drawing step that is needed are referred to as the redrawing operation. So we can simply write it in two lines. If the shape change required is too severe, or the shape change required for the part design is too severe, the drawing in multiple steps. So these additional steps they are termed as a redrawing operation. So when the part design indicates a drawing ratio is too large to form a part in a single step, if we are performing a drawing operation to get some part geometry, and if that geometry determines that the drawing ratio is too large to perform the drawing in a single step, then we will perform the redrawing operation. But for that to take place, there are some general guidelines for performing the redrawing operation. The guidelines for the redrawing would be: for the first draw, the maximum reduction should be of starting blank should be 40 to 50%, 40 to 45%. For second draw, if we are performing the second step of the drawing operation, and the maximum reduction should be in the range of 30%, at most 30%. And for the third draw, it should be around 16% at most. So these are some general guidelines when we are performing the redrawing operation. In the case of the first step we can have a reduction of 40 to 45%, and in the case of the second draw it can be up to 30%. In the case of the third draw we can have the reduction up to 16%. Then there's another specialized type of the drawing operation that is known as the reverse drawing. This one is called as the reverse drawing operation. So what the reverse drawing operation is, it's a related operation in which a drawn part is positioned face down on the die, so that the second drawing operation produces a configuration as shown in this diagram. Once we have performed the drawing operation, so we place the part over the die cavity in the inverse direction, such that it is facing downwards, so we can perform the drawing operation. Although it may seem that in the reverse drawing it would produce a more severe deformation than the redrawing. Visibly you may assume that the deformation severity in this case is more than the redrawing operation, but that's not the case in reality. Why is that so? Because in the case of the reverse drawing, if we see here, the metal is facing downwards and the drawing is also performing downwards, so the direction for both of them is same, so it is easier for the metal to flow in the same direction. The outward direction is same and the inward direction is also same, so it is easy for the metal to flow in the same direction. While in the case of the redrawing, the metal is bent in the opposite direction, so the outer metal is in this direction, the metal towards the inside is in the opposite direction, so the metal faces some strain hardening and some tearing while performing the redrawing operation compared to the reverse drawing. So there's less strain hardening in the reverse drawing, and also the drawing force is lower. So we can cite some general characteristics. It has lower drawing force compared to redrawing, and it has less strain hardening compared to redrawing operation. Then there's a third one, that is the drawing without the blank holder. As you can see, there is no blank holder here. There is no blank holder here, like in this case. So that is a drawing without the blank holder. So one of the primary functions of the blank holder, as we have seen in this one, is to prevent wrinkling. As you know, the wrinkling, because when the outer parameter suddenly reduces during the drawing operation, the wrinkles produce in the walls of the cup we are drawing. So one of the primary function of blank holder is to prevent the wrinkling to take place in the wall of the container or in the flange part. So the tendency of the wrinkling is reduced as the thickness to the diameter ratio of the blank increases. As we know that the thickness to diameter ratio should be greater than 1%, and we have seen this as a feasibility factor for the drawing operation, and the tendency of the wrinkling will reduce as this value increases, right? So if the t by d ratio, the thickness to diameter ratio, is large enough, so we can perform this drawing operation without the blank holder. So as a determining or limiting condition, we have estimated or empirical method to determine this when we can perform the drawing without the blank holder. That is, you can say it as a condition perform drawing without holder. What is the condition? We have dB, the die of the blank, minus dP, die of the punch, equals it should be less than 5 times of the stock thickness. This is the condition for the drawing operation to be taken place without the blank holder. So the draw die must have the shape of a funnel. It should have a shape of a funnel like this one, to permit the material to be drawn properly into the die cavity. So it has somewhat larger corner radii compared to these one in the previous one. So when drawing without a blank holder is feasible, it has the advantage of low cost of tooling. Obviously we don't have the blank holder, so it ultimately reduces the cost while performing the drawing operation, and we ultimately have a simple press that is used for performing the drawing operation without the blank holder. So now we'll move towards some defects that commonly occur in the drawing operation. The first one is a wrinkling in the flange area. As we have seen, what is the flange? The flange is this, the something that is bent at a 90-degree. Right? We have seen this again and again. So one of the defects in the drawing operation that usually occur, that is a wrinkling in the flange area. And the wrinkling in a drawn part consists of a series of ridges like this one. There are a series of ridges that form radially in the downward in the underdrawn flange. It is radially in the underdrawn flange. The underdrawn means the part of the metal that was not able to be drawn into the die cavity, and why it occurs due to the compressive buckling. Because of the compression, the high amount of compression between the blank holder, as we know there is a blank holder here and that die cavity here. So because of that compression, this metal was not able to be drawn into the die cavity. So ultimately we have a ridges in the flange. The second one is the wrinkling in the walls. If and when the wrinkled flange is drawn to the cup, these ridges appear in the vertical wall. Right? If you've if you draw this ridges into the cup, obviously this will be visible in the wall also. Then there's another defect, that is the tearing. And tearing is an open crack in the vertical wall, like in this case, and it usually near the base of the drawn cup. It mostly occurs near the base of the drawn cup towards the punch end, and it occurs due to the high tensile stresses. We can write it occurs due to high tensile stresses. Right. And that causes and these high tensile stresses causes thinning, as we have seen earlier in the last lecture, and ultimately tearing of the material. So this type of failure can also occur as a metal is pulled over a sharp die corner. So it's not only due to the tensile stresses, although that is a primary factor, but when we have the die corner very sharp, as we have seen in the first slide of the drawing operation, if the die corner is very sharp, so there's a possibility that there will be a tearing at the downward edge of the drawn cup. Then there's another defect that is called the airing. This is the formation of irregularities or the airs like this one, air like profile in an upper edge of the deep drawn cup, right? And this is the cause of the anisotropic behavior in the sheet metal. If the material is perfectly isotropic, then this won't occur. Right? Anisotropy, as we have discussed earlier, anisotropic means when the material has a directional behavior, that it is behaving uniformly in particular direction while it is behaving differently in the other direction. Isotropic means it is behaving equally in all the directions. Then there's some surface scratches, very common one. It can occur on the drawn part if the punch and die are not smooth or if the lubrication is not sufficient. So this can cause because of lack of lubrication or non-smooth surface of punch and die. Like airing due to an isotropic behavior of sheet metal. You don't have to remember the long paragraph for these defects. You just need to know the primary cause that are the governing factor for the defects to take place in the drawn cups. So even the single line suffices in the paper if you write the primary cause of the defect. So that's all for the defects in the drawn parts, and now we'll move towards some specialized sheet metal forming operation that are performed by different kinds of tooling. So we know that in addition to the bending and the drawing, some other process can also be performed using conventional presses. So if you're using the metallic tooling, so some specialized processes are the ironing, coining and embossing, lancing and twisting, and with the rubber tooling we have the Guerin process and the hydroforming. So we will start with the ironing and the coining and embossing. So some other operations performed with the metallic tooling. The first one among them is the ironing one. So in deep drawing, the flange area is compressed by squeezing action of the blank perimeter, seeking a smaller circumference as is drawn towards the die opening. As we know that we have the die and it has a blank over it, and there's a punch that is drawing the sheet metal into the die cavity. So the larger perimeter of the blank is becoming moving toward the smaller perimeter. So there's a squeezing action, there's a compression towards the outer edge of the blank, and due to this compression the blank becomes thicker as it moves inwards. As it moves inwards, this blank becomes thicker. So if the thickness of the stock, if the increased thickness of the stock is greater than this clearance, if this increased thickness of the stock is greater than the clearance, then the ironing action takes place. It will be squeezed between the punch and the die. So the metal will be squeezed like this one between the punch and die. So this action is known as the ironing one. Sometimes ironing is performed as a separate step after the drawing operation, the primary drawing operation. Then you perform the ironing one to have a uniform wall thickness. So the drawn part, whatever the product we are trying to achieve, has a longer and a more efficient in terms of the material usage. Some common examples that are used are the beverage can, the ammunition shells. They are two very high production items and they involves the ironing action. Then the second type of this such process is the coining and the embossing one. So coining, as you remember that we have discussed this one, the bulk deformation process, as a subtype of forging operation, right? So it is frequently used in the sheet metal working to form indentation in the raised section as well, right? So this the similar method is used in the sheet metals as well to form some indentation in the raised section. So the indentation result in thinning of the sheet metal and the raised section result in the thickening of the sheet metal. And the second type is the embossing one, which is similar to the coining. It is a forming operation used to create indentation on the sheets, such as raised or lettering or the strengthening lips. As you must have seen, there are some iron covers over the some main lines, and there are some words written over it like KMC or in our city or CDA. So they are the type of embossing process that is performed on those iron covers. This, however, embossing dies possesses matching cavity contours. In the embossing one, we have some matching cavity like this one that is present in the punch and die. Uh, the punch is the positive one and the die is the negative one, as we have discussed earlier, whereas the coining dies may have quite different cavities in two die halves, thus causing more significant metal deformation than embossing one. The coining, as we have discussed, is the bulk deformation process, so the rate of deformation or the amount of deformation in the coining is more than the embossing one. Amount of in coining is more than embossing one. Then the another type of the sheet metal working that is performed by the metallic tooling is the lancing and the twisting one. So the lancing is a combined type of the sheet metal, that is a combination of cutting and the sheet metal bending, or you can say sheet metal cutting and the forming operation. It is performed in a one step to partially separate the metal from the sheet, like this one. Several examples, common examples for the lancing one is like the as we have seen the vents in the heating system, as we have seen the vents in the heating system. So they are the types of the lancing one, the lanced vents in the air conditioning systems. So another process that is performed is the twisting one. So twisting subject the sheet metal to torsion loading rather than the bending load. so we have some torsional load produced here rather than the bending one, and thus causing a twist in the sheet over its length, right? So we have some twisting effect over the sheet along the length of it. It is used to make propeller blades and the fans. As we have seen, the fan blades are somewhat twisted along an axis. So these are some common operations or the processes of the sheet metal working that are performed using the metallic tooling. Then those processes that are performed using the rubber tooling, the first one is the Gurin process. As we can see here, we have the punch having the rubber pad, and we have the blank here with some forming block. So what happened in this Gurin process, it uses a thick rubber pad and or any other flexible material to form a sheet metal over a positive block. So it bends this blank over this forming block. So the rubber pad is confined in a steel container. So this is made up of steel. So the rubber pad is confined inside this steel container. So as the ram descends towards the blank, the rubber gradually surrounds the sheet like this one. So it applies somewhat uniform pressure to deform the shape of the forming block. So it is limited to relatively shallow forms of the shallow sheets, because the pressure developed by the rubber is up to 10 megapascal, right? So we have the pressure up to 10 megapascal. In this case, so which is not sufficient to prevent wrinkling in the deeper formed parts. So the parts that are formed using this Gurin process are not very deep, they are somewhat shallow because of the lower pressure that could be generated using this process. So what is the advantage of the Gurin process? So the advantage of the Gurin process is that it is it has a low cost tooling. The form block can be made up of wood instead of expensive metallic dies. Or the plastic or any cheap material. The rubber pad can be used with different form blocks. So the same rubber pad can be used with different blocks. Of different blocks. I'm just writing blocks here with different forming blocks. So these factors make rubber forming attractive in a small quantity production, such as the aircraft industry, and whereas the process where the process was initially developed. So this process was developed in the aerospace industry, and obviously it suits to that industry where we don't have the very large amount of production, rather small but a specialized amount of production. The second type of operation that is performed using the other than metallic tooling, that is a hydroforming. And if you remember, we have already studied a process similar to this one, that was the hydroforming extrusion process, in which we apply the pressure using the liquid onto the billet in the extrusion process. So the hydroforming is similar to Gurin process. The difference is that it substitutes the rubber diaphragm with the liquid, with the hydraulic fluid. So in place of the thick rubber pad, this allows the pressure to form to be exceeded up to 100 megapascal. So the pressure in the case of the hydroforming ranges up to 100 megapascal. Thus, in doing so, it prevents a wrinkling in the deep formed parts. In the case of the Gurin process, we cannot make the deep cups, while in the case of the hydroforming, we can make the deep cups because of the higher pressure. In fact, the deeper draws can be achieved with the hydroforming process than with the conventional deep drawing. So even this can achieve the deeper draws compared to the conventional deep drawing, which we perform using the metallic tooling. And this is because the uniform pressure in the hydroforming forces the work to contact the punch throughout its length. So it increases the friction and reducing the tensile stresses. So this is because the uniform pressure in the hydroforming uh, forces the work to contact the punch throughout its length, right? So it is in contact with the punch throughout its length, uh, thus increasing the friction and reducing the tensile stresses. So that's why, because of the reduction of the tensile stresses, there is a less chance of tearing of the material at the base of the cup. So these were some specialized processes that are performed using the non-metallic toolings. So that's all for this lecture. In the next lecture we are going to look into some dies that are used for the sheet metal working operations, and different type of dies based on the geometry and based on the power mechanism that they use. And there are some specialized sheet metal operations that are not performed on the presses, that are performed on some specialized tooling.